let's start with probably the oldest and most reliable type of enolate alkylation. This was the first of our series of reactions that use a beta dicarbonyl compound, as we'll see in a second. So what the malonic ester synthesis does is it makes substituted acetic acid. So remember what acetic acid is, right? It's CH3 C double bond OH is acetic acid. So a substituted acetic acid has some R group attached to the alpha carbon. So remember that if the product you're creating has acetic acid with something else attached to the alpha carbon, it could be a long chain carboxylic acid that we make. It could have two alkyl groups at the alpha carbon. Understand that you can make that by the malonic ester synthesis. So the R group comes from an alkyl halide. It's an alkylation, just like we see. So the substance we're going to start with is diethyl propane dioate, or diethyl malonate. So malonic acid is the 3-carbon dicarboxylic acid. Okay? So propane dioic acid, that's malonic acid. So diethyl malonate, the core of it is the 3-carbon carboxylic acid, but it's a diethyl ester. Looks like that. Okay, so it's going to be abbreviated ETO2C, CH2, CO2ET, right? So it's a beta dicarbonyl compound, so the alpha hydrogens are going to be extra acidic, meaning we do not need LDA to deprotonate. We can use ethoxide, something much milder. We do need to use ethoxide, for instance, because we want this R group, right, in the ethoxide to match the R group of the ester. Right, it turns out. If those are switched, we'll have swapping of our R groups. In this case, in this particular synthesis, it's not such a big deal since we're going to hydrolyze the ester at the end. But still, it's just a good habit in general if you're doing a base catalyzed reaction with ester like this to use the same. If you want this to act like a base, if you want it to deprotonate that alpha carbon, just have the same R group there. So look what happens. First, we start out with the malonic ester, right? That diethyl malonate. It's a beta dicarbonyl, so it's deprotonated with alkoxide. So here we have the enolate. Sodium's the positive counterion. We don't always have to draw that, but we have a C- here on the alpha carbon. React that with a primary alkyl halide, and we get an R group now alkylating that alpha carbon. So there it's alkylated. Now, how do we get from here to a substituted acetic acid? Well, we have this alkylated malonic ester. It's just drawn a little bit differently here. So it's got these two CO2ET groups sort of off to the side. What we do is react it with aqueous acid and heat. And remember, we draw heat with the triangle or the delta sign like that. So what that's going to do, it starts by hydrolyzing the esters into 2 carboxylic acids. So that's a intermediate, right? RCH, CO2H, and CO2H, as we'll see on the next page. And then there's a decarboxylation reaction where we lose carbon dioxide from the molecule. So let's look carefully at the decarboxylation, how that happens, right? So here's our diacid. Okay? This is a view of what happened after we had the diester, which we hydrolyze. So diester, just like any ester, gets hydrolyzed into a carboxylic acid. Now, any CO2H, any carboxylic acid that's beta to a carbonyl, okay? We're going to look at it this way. Here's CO2H, here's alpha, here's beta. We look for beta keto acid. Let's actually say this, that any beta keto acid can decarboxylate. Okay? It requires heat to drive carbon dioxide off. A diacid is considered a beta keto acid, right? It just has an OH here on the other side of the beta, right? What happens is a cyclic reaction, right, with the 3 arrows, a lot like the McLafferty rearrangement, where the carbonyl of one attacks the H of the other carboxylic acid. Electrons come down to make a new CO double bond. Carbon breaks. We end up with an enol right here, which tautomerizes to the keto form, which in this case, because we still had that OH attached to the carbonyl there, we end up with a carboxylic acid. So really anything can be over here on the other side of this beta carbonyl here. As long as we have a carboxylic acid over here, this could be a ketone, right? That'll decarboxylate also. Let's just look at a quick overview here of this malonic ester synthesis. Let's say I have our malonic ester, right? Here's our diethyl malonate or propane dioate with 1 bromobutane in the presence of our base, right? What happens? It deprotonates alpha and then alkylates. So here we have the alkylated malonic ester. Hydronium and heat will first hydrolyze, then decarboxylate. So we end up with, instead of 2 esters, we have just 1 carboxylic acid and an additional H on that carbon. Now, if we want to, we can add 2 R groups to that, right? So after we do the first alkylation, instead of doing the decarboxylation and so on, if I do the first alkylation and then react with base again and another electrophile, I can alkylate a second time. So I can get 2 alkyl groups right here. They can be the same or they can be different. It doesn't matter. You do them one at a time, one after another. You can get very good conversions of the dialkylated product. So here we have 2 alkyl groups. We do the same thing where these 2 esters become the 1 carboxylic acid. And look, there's the new H that came onto that alpha carbon in the decarboxylation process, right? Really, it's when the enol tautomerizes back to the keto form that we get that new H there. So that's the general form of the malonic ester synthesis. You use it, just like we said, to make substituted acetic acid, in fact, right? So up here, we had hexanoic acid. We started with the 4-carbon alkyl bromide, which alkylated the malonic ester, and that turned it into the carboxylic acid, right? This alpha carbon here was the alpha carbon of the malonic ester, and the C double bond OH carbon was the carbon from one of the esters in the malonic ester starting material. We can use the malonic ester synthesis as a very good way to make cycloalkane carboxylic acids, right? Remember, a cycloalkane carboxylic acid is a ring and then C double bond OH outside of the ring. So watch how we'll do this from a dibromoalkane. So here's our malonic ester that we've deprotonated. This is 1,4-dibromobutane. So the enolate will displace one of the bromines, okay? So it alkylates, right? But then, if you have an excess of base in there, which you'll need for this, we can deprotonate again at the alpha carbon, and it will attack the other bromine in that dibromoalkane. So that makes our 5-membered ring. We start by just a regular SN2 reaction, then after that it is intramolecular. Right? The C- attacks the carbon and displaces the bromine that's part of the first alkyl group that added on. So that made a 5-membered ring, right? It's a diester on that alpha carbon, and then our decarboxylation chain will essentially get rid of one of the ester groups and then change the other one into a carboxylic acid, right? So hydrolysis makes a diacid, decarboxylation, right? So let's trace a carbon here. The carbon of one of these ester groups is now the carbon of the carboxylic acid. Okay, so that gives away carbon dioxide. We also have ethanol that's been given away as part of the hydrolysis, that first thing that happened. So we made a 5-membered ring here, so we used 4-carbon dibromo alkane. Right? Why is that? Let's trace these 4 carbons from the dibromo alkane into the product. Right? They're the 1, 2, 3, 4 secondary carbons in the ring. The carbon in the ring attached to the C double bond OH is the original alpha carbon from the diester. Okay. So that's how you follow it along. We still made a substituted acetic acid, right? Here we've got our 2 carbons originally that came from our malonic ester. We now just have a ring that's attached twice to the alpha carbon. It's the same sort of deal, right? So that 5th carbon in the ring came from the malonic ester, so it should hopefully make sense that if we want to make a 6-membered ring, right, if we want to make the 6-membered cyclohexane carboxylic acid, we should understand that the C of the carboxylic acid as well as the alpha carbon come from the malonic ester, and then everything else will come from the dibromo alkane. So if I do this retrosynthetically, I'll have a 5-carbon, 1, 2, 3, 4, 5-carbon dibromo alkane plus the malonic ester. So here's our CO2ET, CH minus CO2ET, right, that we get from deprotonating the malonic ester. So look what happens. The alpha carbon, let's label it, alpha carbon will displace one of the bromines. It doesn't matter which one. The other bromine is still intact, but we've now made a new carbon-carbon bond, which will be CH, CO2ET, CO2ET. Deprotonating that again, OET minus, takes off the remaining alpha hydrogen. There's 1, 2, 3, 4, 5. Last carbon was our alpha. So that's a C minus, CO2ET, CO2ET. That then will displace the other bromine. We have our 6-membered ring, but instead of cycloalkane carboxylic acid, I have 2 ester groups attached to what was originally the alpha carbon. So hydronium and heat will, remember, just like we said, remove one of the ester groups, convert the other into a carboxylic acid. So really they both become carboxylic acids. Then there's a decarboxylation, that cyclic transition state that gives us our cycloalkane carboxylic acid, C double bond O, OH. Okay. A similar, very closely related synthesis is the acetoacetic ester synthesis. Really just the same in pretty much every way as our malonic ester synthesis, except it makes substituted acetone. Right? So acetone is just the 3-carbon ketone. Here, our product is acetone with some R group attached to the alpha carbon. So, especially alpha substituted acetone. Okay? So, it can have 1 R group, it can have 2 R groups, it can be a ring. So, this can make a methyl ketone that's external to a cycloalkane ring, just like we said. So, let's start with this. Our starting material in the acetoacetic ester synthesis is ethyl acetoacetate. Okay? Why is it called ethyl acetoacetate? If I had just ethyl acetate, it would be ETO C double bond O, CH3, like that, right? ETO, C double bond O, CH3. That's ethyl acetate. Ethyl acetoacetate, or acetoacetate, I don't know how you want to say that, has an acetyl group, right? So has an additional C double bond O, CH3 attached to the alpha carbon originally. So it's, again, a beta dicarbonyl compound. It just has a ketone on one side and an ester on the other side. Okay, that's it. Our malonic ester had ETO on both sides. This just has a CH3 where one of the ETOs was. That's it. Okay, so exact same thing happens. We deprotonate alpha. We alkylate alpha. So here we have a monoalkylated acetoacetic ester. The alkylated compound is hydrolyzed. I'll redraw it the way that that we started up above, actually. C double bond O CH2, C double bond O CH3. Okay, with an R group and an H. By the way, if we wanted to alkylate a second time here, we also can. Okay, so first thing that happens, ester hydrolysis, H3O+. Right? Remember, this is acid catalyzed, so you have to go back to our last chapter where it says that the carbonyl is protonated first. Okay? Water attacks, there's a proton transfer, and then ETOH gets kicked out as a leaving group. So you end up with a carboxylic acid. Everything else is the same. I'm going to redraw it a little bit just so that we can successfully decarboxylate. I'm going to make OH. I'm going to make the H of the carboxylic acid point up towards the other carbonyl. Right? Otherwise, totally the same. H and R. Okay. Then come our 3 arrows. So I like to start in the carbonyl and have that attack the H. That makes a CO double bond. We break a CC double bond. Our product is an enol. CH3, R and H. The enol tautomerizes to the methyl ketone. Okay. So again, all we did was alkylate at the alpha position, and then we essentially just got rid of that extra ester group by first making it into an acid and then decarboxylating. Right? That's it. So don't don't get lost in the details of this. Make sure you can successfully understand how we started here, right? We started with the acetoacetate. Okay? The ester group ends up going away, and we end up with just a new R group attached, right? So these 3 carbons, use a new color here, the alpha carbon, the ketone carbonyl, and the CH3 are still present, right? Alpha carbon, ketone carbonyl, and CH3. Okay. We've added an R group to the alpha carbon. We've hydrolyzed and decarboxylated to remove that extra ethyl. Okay?